It could be a region in this area, it could be per household. So what has to be done is urbanEXODUS has to be capable to deal with this. And it's similar with hazards. So when we get hazard data, it could be polygons, it could be cell data, it could be the fire front. So in each of these models, urbanEXODUS has to be able to deal with these different file formats and inputs. And that's what I'm going to talk about in those two. And if I get time, I'll then start talking about mixed modal, where those are larger scale evacuations, where vehicle has become an important factor. And the first case I'm going to look at is a small town where traffic congestion isn't necessarily a problem. And then I'm going to look at more of a city area where it's denser population, and there you have to also direct the traffic. So the main difference between the pedestrian and the vehicle one is in the vehicle one, you've got two different strategies, one for the pedestrian and one for the vehicles. So urbanEXODUS is what's under the bonnet when you see WebEXODUS. So this is running in the background, but you can actually use it directly, and that's how we often use it in-house, directly. So the main thing, well, basically we've been developing pedestrian models since for over 25 years now, and we started off working for aircraft, buildings, and maritime areas. So this part here is like the basic system. And for the urban scale, we've extended the hazards, so we can take in things like fire, floods, and urban scale fires. We did fire modeling before in the pedestrian. And then for the traffic, we then bolted on this thing, which is a SUMO simulation module, which is a third-party application that simulates the traffic. Now, EXODUS doesn't directly model the traffic at the micro level, at the individual level. We let some other third-party application do that, and in this case, it's SUMO. But I must add that urbanEXODUS controls the high-level behaviour of the vehicles as well as the pedestrians by deciding when they evacuate, where they go, what route they take. And it also takes control when there's interaction between the pedestrians and the individuals. So when a pedestrian wants to cross a road, EXODUS will then tell the vehicle it needs to either slow down or give way, or which one has priority. And also, the feature we got in what we've added to EXODUS for the pedestrians is the ability to consider urgency when they cross the road. Because in an evacuation scenario, we believe that urgency could be a major factor on how people interact. You've already seen this slide before, and this one just talks about the hazards. I was just going to say that EXODUS has been extended for flood, chemical spills, wildfire, and spreads. And we can read in different hazard formats that I previously mentioned. It also will work out fatality levels and make zones impassable if they've been burnt. And also, it will estimate injury levels or how much time somebody's been exposed to a gas. So for instance, if they're going through a certain chemical gas that doesn't have an instantaneous effect on them, it will work out how much time they've been exposed to those various gases. So the key thing about that is, in those situations where chemical attack is not necessarily the fastest simulation is the best, it's the simulation which is the safest. So you want to minimise people's exposures to the hazard where possible. So here's my first example, and this one is looking at an area which is about kilometre by kilometre, and this is, we're looking at pedestrian evacuation because this is the old town of roads, and in there's not much, well, there isn't much vehicle access, so the primary method of evacuation here is pedestrian. And in this one, we got some information, so we've got two populations off peak and peak times. So we've got some information, response time distribution. So I don't know what notification method is being used here, but we just know that when the alarm or the call to evacuate goes off, people respond between a particular time frame. So here we have the scenario. So they have these zones, and each people in these zones have to go to these evacuation points. And then when they're at those evacuation points, the authorities can, at some point, say whether the individuals should evacuate the area or they can return to go back to their place of abode. So how do we specify this in EXODUS? Now, when you use WebEXODUS, you don't see this under the bonnet, because we want EXODUS to be very flexible, so we have a scripting system that's hidden. Now, WebEXODUS generates these scripts. You don't notice. And here, in these scripts, we load up the population, the geometry, and here we specify about the population. And then when I talk about those polygons, we have a list of points here. So we say this is the population area for the medieval city outline. We tell how many people are in percentage of populations in buildings, highways, which is on the streets, and we specify how much is in the open spaces. And then we give them response time. So in this simple system, simple notification, we say people respond between 60 seconds and 900 minutes, which is 1 to 15 minutes. And we give them a travel speed attributes and a walk rate. And then we give them itineraries to say all the people in this area go to this particular wait location. So we're specifying that, and then what happens in this scenario, this script, is that after a certain time, they then evacuate. So this is the evacuation scenario. So here we have the software running. So you've been using WebExodus. This is what it looks like in Exodus. We enlarge the people so we can see them. So these large dots, they've been enlarged about tenfold. So we can see where the people go. They go to their assembly stations, which are there, and they congregate. And then after a certain time, it then tells them to evacuate. So this model here assumes a perfect evacuation. There's no hiccups or no issues. This is just testing the procedures or whether that method works. If you wanted to go into detail and say, oh, well, what if it's scenarios, you would have to build that into the model. So if you had a conversion route or an evacuation route, you need to consider that. So in the ideal situation, the evacuation starts, so the evacuation process ends after 31 minutes, which is quite impressive to evacuate an area. But you've got to remember this is like a perfect scenario, and we're just testing the strategy. So that's all good, so that's a simulation, but what do we get out of this? So when we run that simulation, we get loads of evacuation performance information which we can use. So we've got here about the elapsed time, how much people spent evacuating, how much time they spent waiting. We have the population totals, and we have for each of the gates, so these are the exit points of how many people exit per each of the exit points from the structure. But the key thing is this, where we can look at congestion levels. So if you're giving your scenario, you can see how much congestion is building up. So for instance, if you've got a moving crowd, you may not want to get more than 3 people per metre squared in a moving crowd, because if you've got something higher than that, you have a risk of trips and falls. So here it's identified this area as red, saying you're getting high density build up here. So you might consider whether you need to change your evacuation strategy or the routes you take and so on. So that's the basic, simple case of evacuating an urban area. So now, let's look at something a bit more complicated. So this was done as part of the IMPREP project, and we looked at Spalessa, and we looked at a chemical hazard. Now, in this one, this has a much more complicated, it's a much more densely population area with the evacuation points, and they want to use a notification system. So there's a chemical event, so there's a truck, there's an issue happens, and it releases a chemical. And during that phase, the authorities want to move people away from the chemical hazard, but they might change that, so they have various standoff distances. And then inside that notification type, they have different notification methods. So they might ring the intercom, where they go around knocking on doors, or they use loud hailers or whatever that is available. And for each of them, you have a response distribution. So here we have the notification zone. So that center point is where the incidents happened. And as time changes, they might need to move people back, and they have standoff distances, so how far they want to move people away from that. And inside those regions, they would then start notifying people to try and make them evacuate. And so that's idealistic. This one shows you the actual layout of the notification zones. I don't know if you can see that, it's the light. So here it is, they've got the areas, but they're not actually round. They could be various polygon shapes. So to model those notification procedures, because notification procedures can be quite complicated, in this one we've got ring the intercom, automatic phone call system and other. And other's supposed to cover all other types of evacuation, which are spontaneous evacuation or people being notified by neighbours, etc. And then we have the standoff distance, the notification zone, as I mentioned, the times for those standoff distances. So for the simulation, we're going to say, at this time we're going to have a standoff distance of, say, X meters. At another time we're going to have further away and so on. And then for each notification rate, notification method, we have a success rate. So when they initially send out the automatic dialer, a certain amount of the population will respond instantaneously to that, or we will respond to it initially in the first X number of minutes. And then after that, you get a cascading effect. As people start to evacuate, they will notify more people, and you have this subsequent rate. So initially it goes up, and then other people start to respond because of that one. So if you send out automatic phone calls, it goes around dialing people. And we got this in families per minute. So this is how we specify ring the intercom. And most people won't need to look at this, because this is what is in Exodus. But that's for the expert user. So you can use the web interface thing and do the basic things, but if you want to dig down and make a very unique situational case, you can then start changing the parameters and live inside urbanEXODUS directly. And here you've got the success rate, ring the intercom, automatic phone call, and other. So we can specify all those values. Here's the different chemical spreads, and here we had 3 different scenarios. So that's one scenario where the wind is blowing from the northeast, blowing down. Then we have one where the wind's blowing from the south. So, and then we have another one here where the wind's blowing in a different direction. And this just shows you the spread of chemicals. And here the chemicals were like concentration, so that's a higher concentration, slightly lower, and so on. I think it was chlorine gas we used in this one. So for a chemical hazard, we use these things called the AEGL levels, which are the acute exposure guideline levels. And what Exodus does is record how much time people have been exposed to each of these levels. So if they've got these higher doses, they may need hospitalisation straight away after evacuating. So we record these different values and how much exposure, and then from that you can judge how successful your population evacuation was by how much exposure individuals have received of each type of gas. So this is it running here. I think the hazard is somewhere around here. And these little dots are all running away from it. This is Pedestrian Base. You've got the graphs going up showing you the rate of evacuation, and as it slowly clears, the notification zones move off, which aren't illustrated in that one. But here's kind of results. So here's the hazard area and hazard spread. These are the areas that you lose. And then you get the total population. The total impact is 6,891 people were impacted by the various hazards. And this is the number of people that got those levels. So most of them are low level. Some of them got a very high level dose, 11 people. And the number of people notified by phone successfully, and so on. So those are so you get all this information out. But I guess the key thing is you want to minimise those numbers, which is your exposure levels to the population. And here's the notification rate, so you can see how successful. So this is the notification. So this is the spontaneous other ones. So with this one, you get people, when incident occurs, people start to evacuate because they can see the event. Here, the ring the intercom is when they start clearing the distance. So this is after the services arrive and they start moving people away, and that's where you have this step effect. And then this is the automatic dialer. It kicks in, and slowly it has less and less effect. So initially it had an effect as people phoned the households, and then that would ease off, level off there. So you get these kind of kinks in evacuation, because this kink here is response time, this is response time. But the thing is that you get more people responding there, the others will start to be evacuated because they see more people evacuating. And that's the, yeah. So that's the kind of pedestrian ones. Now let's look at the vehicle-based cases. So this is our Marysville example. And now you covered this, haven't you? You didn't do this one. So this one, we're looking at a fire spread, or a fire case scenario, in a rural town area. And here we have, this is in WebEx showing you the fire spread, these isochrones in the fire. And I think we used the Phoenix model here to generate that fire scenario. And we're having various assumptions saying when to evacuate the people after the fire starts. So this is what it looks in Exodus when we run it. And Exodus is drawing the fire isochrones as they spread. This is about 1 hour, 9 minutes in. the red bit's the older parts of the fire, and the front, as it progresses, it just shows as it furs out. So these bits are burnt for some time beforehand. And if we zoom in, you can start to see, here's the vehicles and here's the pedestrians. Go back. So we enlarge the car so we can see where they are and move around, and the pedestrians. In WebExodus we use density contours, which are probably easier to see, but here we're just enlarging the icon so we can see the people moving. So from that simulation, we can start to see how much time it takes to evacuate the people so many hours after the fire. And for the pedestrian one, we can get some numbers saying if you did a pedestrian-only evacuation, that's how long it takes to take there, 2 hours 16. For the multimodal one, you get with vehicles only, it's obviously a shorter time, 1 hour 36 after the fire starts. And for the mixed one, multimodal, it's a bit longer, 1 hour 57. But I forgot to mention that in this one, the vehicles were sent north, so people in the cars, they would go up, they would drive up north and exit, and the pedestrians would go to this assembly area called the Oval, where they would wait there for further assistance. So the pedestrians were going there, and the vehicles were going up and driving north away from the fire. That was shelter in place there. So that was the Maryville fire case. Now we look at another situation, which is a flood scenario in the Netherlands, where we look at a more densely packed urban area. And now what's important here is how do we route the traffic? So here is the old town here, and that's quite densely populated, and also it's not very good for the vehicles. So it's easy for pedestrians to walk out that way, but for vehicles it would create a lot of congestion. And we had to run this simulation many times to try and figure out what was the best way to route the vehicles. So the best place for the vehicles is to go out these ways, here and here, because they are major roads and they can take traffic. So we tend to route the vehicles away from that. So we came up with this strategy for redirecting the vehicles. So this zone here, these people go out that way. The vehicles here go out that way, exit 5, this one. And just a small zone here with target 2. The cars already in the old town can actually evacuate over the bridge. So this was higher land, this is lower land, and this is floods. So the scenario here is we have a flooded scenario, and we have a dike that can be breached. The ship, basically a boat crashes into it, and the authorities have got to make a decision what to do and when to evacuate. And in our scenario, it's heavy rain, the boat crashes into it, they have to fight it, holds for a bit longer, and then it breaks. And then there's 10 hours left until the water breach, so risen by the storm to agree of being able to make the levee collapse. So it's 10 hours after the boat crashes into it, the thing collapses. And the storms effectively arrive at that time. And this is where we had the flood data, and this flood data was cell-based. So we got all the data about the water levels at different cell levels, and we had to convert that to isochrones, which are these polygons at different levels. Then we looked at it and said, right, when the water level goes above a certain depth, we say the people can't evacuate and they have to do a vertical evacuation. So in this one we've got two scenarios. We've got a horizontal and a vertical evacuation where people will go up a floor in their house or building. This is the notification zones where people get notified. I think they will send out text messages or something, an automatic dialer. And on this scenario, they had these zones here. These zones would be notified first, and then they've decided this would be 15 minutes after the initial notification of these zones. So once they decided for the evacuation, they would clear this area, they would notify this area first, and then 15 minutes later there. And this area is more industrial, less densely populated. So again, this is what you can see in Exodus. Exodus is looking more like WebExodus every day. It's getting more and more detail about the buildings, the geography around it. And then often we switch that off because when you're looking at this information, it's too detailed. So we start to use these outlines. And again, we have the vehicles, we have the pedestrians moving around, which you can see there. Those are the cars and the vehicles moving. So we're mixing the two together. And then when they come into contact or when they want to cross the roads, pedestrians have to decide how they respond. So we've got various models for that. So that's covered in a different talk. They have papers on that as well. So these are sort of results or the time. So we get some times for evacuating, and these are in hours. So evacuation time 6 hours 59 minutes. Average time spent evacuating 1 hour 47. So we're getting these numbers out for different pedestrian scenario, vehicle pedestrian scenarios, and then we've got pedestrian only evacuation as well, just for comparisons. They just try to compare how long it takes to evacuate that area by pedestrian. The thing is, when the pedestrians are, they've got less distance to walk, so the cars isn't out with the major roads. So that kind of brings me to the end. So that's the 4 cases, and the 4 basic features of urbanEXODUS. And just to mention, we are working on a VR equivalent, so we've got a 3D map, and this is our 3D map of the cars and the people. And this is Kempen in 3D, we've got the pedestrians walking out. And that's kind of work in progress at the moment, so we can get a 3D flying pass for it. So the key thing is, the novelty of urbanEXODUS at this stage is integration of pedestrian, vehicle and hazard model into one unified system. And that's unique, but getting the hazards in is quite a manual process at times because of the different formats they come in, and the notification process takes a bit of time. And that's probably where we've got to work more on, is develop interfaces and areas to improve that, how we get this information in and make it simpler. And we've got the hazards of chemicals, fire and flood, so we've looked at those 3. And we've got this pedestrian interaction behaviour, which is a feature that we've been considering. Well, many vehicle models wanted to include that, and they say urgency is important for vehicle pedestrian models, especially in rush hour scenarios. But we've actually developed it for evacuation scenarios. And that's why I say ours is first of all consider urgency and risk in that interaction. And as we've demonstrated, it can be used WebExodus for a couple system for planning and preparing for urban evacuations, and also for training, which is there. But this is the area that's really is work. There's work on validation is always ongoing, so we're constantly getting more information. So with those intercom systems and notification systems, we haven't got any hard data. What we had to do is poll the experts and say to them, how do you think these systems work? How do you think people respond? And we get their feedback. So we've got based on the best available information we have at the moment, but we haven't got quite detailed studies. But that's all programmable now, so we can put in whatever parameters is available at a later stage. Right. Okay, I think that's it for now. Thank you very much. That's it.
Well, that brings a close to proceedings for today. Unless